Welcome. No matter who you are, if you're interested in programming, this video will be your very first lesson in getting started with coding. Before we dive in, I want to take a few minutes to explain why, even though AI can already assist with programming, you still need to learn programming yourself. This is especially important if you're someone from another field attracted by AI programming. You've probably heard something like this. With the help of AI, you can easily create an app without any programming knowledge. This is the most common pitch used by AI coding tools, but it's actually not quite reasonable. Handing powerful tools to someone who lacks the necessary theoretical knowledge is a dangerous thing. Let me give you an easier to understand example. Imagine someone with no architectural knowledge suddenly gains the power to command a construction team. The team follows their orders faithfully, and this person instructs them to build their ideal residential skyscraper. Now, would you dare live in that building? Personally, I wouldn't. Because this person has no knowledge of architecture, they might design something that doesn't meet safety standards, missing fire safety measures, poorly planned plumbing and electrical layouts, or even misjudging the building's load-bearing capacity and structural strength. As a result, the building carries many hidden risks caused by the commander's lack of expertise. Programming is the same. Programming is a very precise and complex craft, a genuinely difficult technical discipline. With AI, sure, you can command it to do the work for you, but if you don't understand programming at all, the tasks you assign might be unreasonable or impossible, like trying to build a perpetual motion machine. Or you might produce something that runs but has security vulnerabilities. For example, I've noticed many AI coders, when developing websites, put their API keys directly into front-end code. This happens because they lack awareness of data security. They just give their idea and let AI handle everything. But data security isn't always something AI will automatically take care of, so this situation arises. If such an app is just for personal use, it might work fine. But once you make it public, the keys get exposed, which can lead to direct financial loss. In short, for now, AI cannot complete complex tasks entirely on its own. So even if you want to leverage AI for programming, I'll teach you how to do it, but you still need a solid, high-level understanding of programming. You might not need to dive deep into every line of code, but you must understand what AI can do for you and be able to interpret what AI is doing for you at any moment. Remember, AI is a tool. You need to control it, not hand everything over and let it control you. Alright, let's get started. Programming is basically writing down the steps needed to complete a task. These written steps are called a program. To help you better understand this concept, let's be more concrete. You can think of a recipe. A recipe records every step to make a dish. It's essentially a program. And writing the recipe is like programming. Programming means writing instructions for a computer to follow in order to complete a specific task. However, computers can't understand human language, so we must use a language they can understand, called a programming language. Learning a programming language is one of the three most important topics in programming, and it's a key focus of this video. The other two topics are algorithms and frameworks, which we will also cover here. First, you need to understand how a computer executes a program. You can think of the core of a computer as consisting of memory and a processor. The memory is like a warehouse with many small compartments, each able to store a piece of data. The processor is like a worker who takes data from the memory, performs operations such as addition, subtraction, multiplication, and division, and then writes the results back into the memory. A computer program is a sequence of steps that tells this worker where to get data, what operations to perform, and where to store the results. You might wonder, based on this model, programming seems like it can only make the computer do math problems. But in reality, computers can do much more than math. How is that possible? In fact, in real computers, some special areas in memory are reserved and designed, so that when specific data is written there, it can control external devices. For example, imagine 3 consecutive memory cells. If you write 20, 10, 1 into them, the computer will light up a pixel on the screen at row 20, column 10. Got it? Although the computer's basic internal operations are still just fetching data, calculating and storing data, by defining these special memory areas and writing the right data into them, programs can do many things 7 affect the real world, like controlling the display, playing sounds, or transmitting data over a network. Keep this computer model in mind, and now we'll formally start introducing programming languages. Almost all programming languages share 3 basic elements: variables, control flow, and functions. If you have no programming background, these 3 terms might sound confusing at first, but don't worry. We'll go through them one by one, starting with the simplest, variables. Remember the basic computer model we talked about earlier? Programming languages are essentially used to describe a series of instructions about where to read data from, how to perform calculations, and where to write data to. In theory, you could program by directly specifying the addresses of memory cells. In some lower-level languages like C programming language, you actually can do this. However, this approach makes programming very cumbersome and even dangerous, because you have to manually manage memory usage. So most programming languages provide a more user-friendly way by giving names to memory cells and letting the system manage their use automatically. For example, here's a simple addition program. If you've studied algebra, you can easily understand what this program does. But from a programming perspective, how is this code actually processed? When the computer executes x equals 1, it automatically allocates a space in memory named x and writes the number 1 into it. When it executes y equals 2, it similarly allocates another memory space named y and writes the number 2. Now, you can use the names x and y to access these memory areas without worrying about the actual memory addresses. When it executes c equals x plus y, the computer first reads the data stored at x and y, adds them together, then allocates a new memory space named c and writes the result there. This practice of giving names to memory cells is what we call variables. Essentially, a variable is just a label for a specific area in memory. You use the name to access the content stored in that area. Once you understand this, you'll also get why some programming instructions can confuse beginners. For example, almost every beginner wonders about this line. Mathematically, this looks nonsensical. How can x equal x plus 1? But in programming languages, this is perfectly valid because equals doesn't mean equals in the math sense. Instead, it means assign the value on the right to the variable on the left. Technically, this is called assignment. Here, x is just a label for a memory location. So x equals x plus 1 means read the current value stored at x, add 1 to it, then write the result back to the same memory location labeled x. The end effect is that the value of variable x increases by 1. Once you learn how to use variables, you can essentially treat a programming language as a powerful calculator. Next, let's introduce control flow in programming languages. Control flow describes how instructions are executed within a program. In fact, you've already seen one kind of control flow in our earlier examples. The code runs sequentially, line by line from top to bottom. This is called sequential flow. But in programming languages, besides sequential flow, there are two other common types, branching and loops. Let's start with branching, using the recipe program example again. Imagine you want to write a mashed potato recipe that suits people all around the world. How would you do it? The challenge is that eating habits and taste preferences vary globally. For instance, people in Western countries might prefer their mashed potatoes sweeter, while people in India might prefer them saltier. So, how can one recipe accommodate these differences? It's simple. You can write it like this. If you like sweet, add butter, sugar, and milk. If you like salty, add salt and butter. This way, the same recipe can take different paths depending on the situation. That's the basic idea of branching in programming. In computer programs, you can use if statements to achieve similar effects. For example here, task 1 will run, but task 2 won't. Usually if is used together with else to create an either-or structure. The rules are, if the if condition is true, execute the code inside if and skip the else block. If the if condition is false, execute the code inside else instead. For example here, the condition is true, so task 1 will be executed. Here the condition is false, so task 2 will run. A handy trick is that when you need to check multiple conditions one after another, you can chain multiple if and else if statements. For example, suppose you want to assign different services to people between ages 20 and 60 based on their age groups. Assuming age is 45, the program will check each condition in order until it finds one that matches, then execute the corresponding task. In this case, age 45 satisfies the third condition, so task 3 will run. Now let's talk about loops, and we'll use the mashed potato recipe example again. When making mashed potatoes, you usually need to mash and stir repeatedly to get a smooth texture. Suppose you need to mash and stir 100 times to reach the ideal result. How would you write this recipe? Would you write mash stir 100 times? Or say mash and stir until you've done it 100 times? Obviously, the latter because stirring is a repetitive action, and there's no need to write the same steps over and over again. Programming works the same way. Often, you need to repeat operations many times, like going through every pixel on a computer screen. Writing each operation one by one would be a huge workload. A better way is to use loops. The general form of a loop is here. This means, as long as the condition is true, execute the loop task once. When the condition becomes false, exit the loop. For example here, task will run 5 times because I starts at 0 and increments by 1 each time. When I reaches 5, the condition 5 becomes false, and the loop stops. You can also to achieve more complex functionality. For instance, this code calculates the sum of all elements in a list. Here's a quick explanation. We define a variable total initialized to 0. I is used to traverse the indices of array. The while checks whether I is less than the length of the list. Array I gets the element at position I. The loop reads each element one by one and adds it to total. When the loop finishes, total holds the sum of all elements in array, which is 15. Here's a bit of computer science theory for you. Using just sequence, branching, and loops, any computable task can be solved. In other words, as long as the task is mathematically solvable, you can implement it using statements like if and while. That's the magic of programming, using simple tools to create infinite possibilities. Finally, let's talk about functions in programming languages. Let's continue with the recipe example. I'm getting hungry just talking about it. Suppose you need to write two recipes, one for fish and chips and another for a burger combo. Both use fries. How would you handle this? One way is to write the fries preparation steps separately in each recipe, but that's clearly not smart because it repeats the same content. A better approach is to write a dedicated fries recipe once, then simply refer to that fries recipe wherever you need it. Programming is similar. We can package useful pieces of functionality to reuse them easily. This package functionality is called a function. Let's take the previous example of summing elements in a list. Now, we want to write a function that calculates the sum of any list. Here's how you define a function named sum, with a parameter called array, that returns the result total after finishing. Now, when you want to calculate the sum of a list, you just call this function and pass the list as an argument. How does it work? Variables defined inside the function, including the parameter, are private and can only be used inside the function. When you call SumArray equals 1, 2, 3, the function's array variable is assigned that value, and the code sums up that list. The variable total is also inside the function, so it's not accessible from outside. If you want the result outside the function, you have to use return to send the result back. That way, you can assign it to an external variable. Finally, you might be wondering, which programming language should you learn? The truth is, it depends on your goals. No programming language is perfect at everything. Each language usually excels in certain areas. For example, Python is commonly used for scientific computing, artificial intelligence, and web backend development. JavaScript is mainly for front-end web development. Java is popular for backend systems and databases. And C++ is often used in operating systems and large-scale games. Here's a complete chart showing the main languages and the fields they are best suited for. If you're not sure what you want to do yet and just want to pick a language to start learning programming, my recommendation is either Python or JavaScript. Both are scripting languages with simple syntax, can run immediately so you can see results fast. If you want to learn Python, you can check out my previous beginner video on Python. I'll also be making a JavaScript beginner video soon. Alright, that's enough about programming languages for now. Next, let's move on to another important topic: algorithms. To understand what an algorithm is, let's start with a map. Here's a street map of New York City. Suppose you want to get from point A to point B. In reality, there are many possible routes you could take. Theoretically, you could even choose to circle around the entire United States before coming back. But if you want to get to point B as fast as possible, only a few routes make sense. What you need to do is find those fastest routes. This is a classic example of the shortest path problem. Algorithm study is essentially about finding a method that allows a computer to solve a given problem as quickly and efficiently as possible. However, for this introductory course, the shortest path problem might be a bit too complex. So, in this video, I'll focus on a simpler example search problem. Here's the problem. Given a sorted list of numbers arranged from smallest to largest, and a target number, the search problem is to find the position of that target number in the list. To keep it simple, let's assume the target number definitely exists in the list. If you were to solve this with programming, you might write code like this. The basic idea here is to start from the first element and check each element one by one. As soon as you find the target, return its index. This is called linear search. For relatively small arrays, this method works fine. But in real-world production, the search problem often deals with lists containing hundreds of millions or even billions of elements. Imagine a list with 1 billion elements. On average, you might need to check 500 million times to find the target. That's extremely costly in terms of computation. So is there a smarter way? The idea is to first check the middle element of the list. If the middle element is smaller than the target, then the target can only be in the right half of the list. The entire left half can be ignored. If the middle element is larger than the target, then the target must be in the left half. The right half can be ignored. By repeatedly checking the middle element of the current search interval, you can halve the search space each time. This method is called binary search. For example, with 1 billion elements, binary search only requires at most 30 comparisons to find the target, far better than the hundreds of millions of checks needed by linear search. Generally speaking, algorithm design is one of the toughest parts of programming because it involves a lot of theoretical knowledge and demands significant time and effort. My advice is this: you still need to understand algorithms, but in actual programming practice, you can delegate the complexity of implementing algorithms to AI. Although algorithms have always been a key topic in computer science, their development has actually been quite slow. Even a seasoned computer scientist might only come up with a handful of new algorithms in their entire career. Take, for example, the backpropagation algorithm that underpins modern AI training. It was theoretically established many years ago and hasn't seen major breakthroughs since. In other words, in most programming scenarios today, the majority of algorithm theory is already very mature and thoroughly validated. Algorithm design in practical work tends to be repetitive, and this kind of knowledge is well suited to being handled by AI often better than humans can. From my personal experience, about 60% of my past workload involved algorithms, But since AI has become reliable at handling programming tasks, I hardly write algorithm code manually anymore. Instead, I focus on final code review and functionality verification. This way, I can accomplish more than twice the amount of work in the same time and devote the saved energy to other tasks. Let me show you an example. I'm currently building an app which uses a sorted list of records. I want a function that retrieves all records within a specified date range. This function can actually find the range efficiently using binary search, then gather all matching records around that range. What I do is simply tell the AI the function's interface what parameters it takes, the function name, what type of data it should return, and the algorithm it needs to use in. The AI handles the rest perfectly, almost never making mistakes. It often does a better job than I would writing the code myself. So my personal recommendation is this. You still need to learn algorithms, but don't focus too much on the nitty-gritty of implementing them. Instead, concentrate more on understanding the application scenarios and how to use them. Define your functional requirements clearly. Let AI handle the complexity of writing the algorithms, and focus your energy on system architecture and creative tasks. This is a highly efficient and reliable way of working in the AI-powered programming era. Finally, I'd like to briefly explain programming frameworks. If you want to build a backend server using Python, you could manually handle routing, data passing, security, and so on, writing thousands of lines of code just to get a simple service up and running. Or you could use a production-ready Python backend framework like FastAPI, which lets you create a basic service with just a few dozen lines of code. A framework is basically a set of common code structures designed for specific programming scenarios. To put it simply, building functionality without a framework is like building a house entirely from scratch, whereas a framework provides you with a model home that you can freely customize and make your own. This table lists some common frameworks, programming languages, and their typical use cases. You should choose a framework based on your goals. If there's a framework you want to learn about, feel free to comment, and I'll consider making tutorial videos on it. It's important to note that using frameworks is widely recommended in programming. Very few people suggest building your own service entirely from scratch, since the cost-benefit ratio is usually very low. Usually, only large tech companies consider building their own frameworks. Unfortunately, AI often struggles to handle framework-based programming correctly. Production-level frameworks tend to update very quickly, and some features may not even exist in the AI's knowledge base. So if you use AI to help with application frameworks, there's a high chance things will get messy, and you might get frustrated dealing with version control and non-existent APIs. Of course, you can use AI agents to get the latest stable information in real time, but this tends to be very costly. Even a simple small program might end up costing you dozens of dollars, and the final results are not guaranteed. You could also run into security issues like those mentioned at the beginning of the video. In fact, most current AI agents are designed to handle specific programming tasks such as web development or scientific computing, and still perform poorly in general-purpose programming. So, if you plan to program with AI, your focus should be on designing the overall architecture of your program, while letting AI handle the specific implementation details. That way, you and the AI become great programming partners. Thanks for watching. I'm Mark. See you next time.